Bismillahirrahmanirrahim. I welcome all of the engineering students, including the Khwaja Farid University Engineering and Information Technology, Rahim Yar Khan students, to the course of Heat and Mass Transfer. This is the first course, in the Heat and Mass Transfer for the engineering students, especially mechanical engineering. This is lecture 8. The other 7 lectures I have delivered already, but I will upload the videos one by one in the later time. This lecture is regarding the transient conduction. A book we followed is Fundamental of Heat and Mass Transfer by Frank P. Incopita and David P. David, 7th edition, but you can take any other edition. The topic is similar. Transient heat transfer. Up till now, up to chapter number 4, we are discussing the steady state heat transfer in one-dimensional and two-dimensional, but many heat transfer problems are time dependent. Such unsteady transient problems typically arise when the boundary condition of the systems are changed. In the previous, we had not considered the time. We had only see the heat transfer in a one-dimensional or in the two-dimensional, but now there are problems just like the cooling of a metal, the quenching processes. These are basically the time-dependent problems. For example, if the surface temperature of a system is altered, the temperature at each point in the system will also begin to change. And the changes will continue occur until a steady-state temperature distribution is reached. That we know, whenever the steady-state value means steady-state means the temperature becomes constant, then up to that point the temperature will change or heat transfer will take place. Objective. What is the objective of this topic actually? Where this is to be applied, the student must know where this technique can be applicable or not applicable. To assess when the spatial variation of temperature is negligible and temperature varies nearly uniform with time, making the simplified lumped system analysis is applicable. So when the spatial means the surface the variation of temperature is not very significant, right, and it varies almost uniform with time, then we make a very simple model which is called lumped capacitance model. And lumped means we're taking mass or overall system together. Obtain analytical solution for transient one-dimensional conduction problem is in rectangular, cylindrical and spherical geometries using the method of a separation of variable. In this, of course, this chapter we discuss the transient one-dimensional heat transfer in different shapes, especially rectangular, cylindrical, spherical, and these type of geometries we will discuss. And then understand why one-term solution is usually a reasonable approximation. Of course, why we will get the solution in only one term. Why it is easy? Because this is easy to understand and of course to find the approximate value of the heat transfer. Okay, let's see. Now we recognize that many heat transfer problems are of course time dependent, such as unsteady and transient problem typically arise when the boundary condition of the system changes. Boundary conditions of the system changes. For example, a hot metal billet that is removed from a furnace and exposed to a cool air stream. In this case, the boundary condition of the hot billet is to be changed, right, from the furnace high temperature to the air stream the low temperature. Energy is transferred in this case from convection and radiation from the surface to the surrounding. Of course, in this case, the heat transfer takes place from the convection and radiation. Energy transfer by conduction also occur from the interior of the metal of the surface. And the temperature at each point in the billet decreases until a steady state condition is reached. To bring the heat from the inside to the surface, of course, the temperature will change within the solid surface. That is, the heat transfer takes place within the material. But we mostly consider only the heat transfer through the convection and radiation. This is the important thing now here. That is the heat transfer from inside of the material to bring the heat to the surface of the solid body. The further properties of the metal will depend significantly on time, temperature, history. But now in this case, of course, as the temperature is varying within the solid material, there are the different properties like density, specific heat, and all these. They are basically now time dependent, and that results from the heat transfer. Of course, because of the heat transfer, of course these properties are to be varied. Thus, controlling the heat transfer is one key to fabricating new material with enhanced properties. This technique, of course, mostly used in manufacturing processes to control the temperature of material, right? So cool in such a way, it is to be cooled quickly, that is a quenching, or to cool it is with some time. Of course, it gives these other properties of the material, and the properties of the material changes by controlling the heat transfer with time. And that is very important property method used in the material manufacturing. So our objective in this chapter to develop procedure for determining what is my objective. The objective, the time dependence of the temperature distribution, that within the solid, that is conduction during a transient process, how the temperature distribution takes place in a solid. That I told you that because from inside to the outside heat transfer from the solid, then the heat transfer between the solid and the surrounding, that is basically convection and radiation. So there are three heat transfers: the conduction within the material, and of course when the solid is exposed with the environment, and there is a heat transfer with the surrounding or whatever the environment, there is a convection and radiation. The assumption, of course, that we made for this purpose, for example, temperature gradient within the solid may be neglected. A comparatively simple approach, one of the very simple approach, that the gradient of temperature, the rate of change of temperature, right, within the solid, we think that is neglected. Of course, there is a certain gradient of temperature, but we assume that it is almost constant. Right, and this technique, we call it lumped capacitance model. Students, please be careful to think that the rate of change, I'm saying that dt by dx, the temperature change within this solid, we say that is almost negligible, and this assumption made is a lumped capacitance method. We are taking the overall complete material, and what is the amount of energy contained. Capacitance means it's just like the capacitor in electrical, amount of energy contained in the material. This may be used to determine and that we can use for the variation of temperature with time. So a system in which the temperature of a solid varies with time but remains uniform throughout the solid at any time is called lumped system, right? So the system in which temperature of the solid temperature is of course varying, but within the solid the temperature remains same at any time, that is called lumped system. So we are assuming that within the solid the temperature is almost constant. So therefore now we focus our study on the lumped system analysis. In heat transfer analysis, some bodies are observed to behave like a compact mass, right? We sometimes think just like you are making a certain material, aluminium or steel, and put into the water. We take whole steel as a lumped or compact mass. Interior temperature of some bodies remain essentially uniform at all times during a heat transfer process. Of course, the interior temperature, which I are again and again talking of, that the temperature of a solid from the inside, right, itself, we say it is constant over the period of time. The temperature of such bodies can be taken to be a function of time only. They are only the function of time, not the function of a position. So heat transfer analysis that utilize this idealization is known as lumped system. It means that the temperature is only dependent Temperature of the solid is only dependent of the time. It does not depend upon the position x, y or z, which provides great simplification in certain classes of heat transfer problems without much sacrifice to accuracy. Accuracy is not to be sacrificed. We get a good accuracy and we get a good approximated results. So here we are taking the whole mass, no change in temperature with position, but only the change in temperature is with time within the solid body. Let's consider. I give you the one practical example where I can consider that the temperature is constant at different positions, where I cannot consider. Let's see, there is a copper ball. If you see, a hot measurement indicated temperature at different positions is 70 degrees Celsius. So it is not changing. Temperature of the copper ball change with time, but it does not change much with position. At different positions, you see this temperature is constant, and with temperature, with time, of course, temperature will it will release the heat if it is the lower temperature environment. But at a different position, temperature is constant. So I can take this one as a lumped system. But if you see another example, which is a roast beet. If you see, a large roast is an oven. If you cut in the half, you will see that outer part of the roast are well done. For example, the outer part you see of this beet is at 110 degrees centigrade. If you go the inner side is 90 degrees centigrade. If you go more inner, you go to the 40 degrees centigrade. Just like you put a certain thing from a refrigerator and put it in the oven or anything. After some time, if you cut and measure the temperature at different and inside, you'll see the outer one as a higher temperature, and you move inner if the temperature is to be reduced. So this cannot be considered because here the temperature is a function of position as well. So therefore, I cannot consider this one as a lumped system. So I think this is understand. So this one is cannot be considered lumped, and of course the copper ball, in which temperature is almost constant at different positions, this can be considered as a lumped capacitance pattern. So a common transient conduction problem is one for which a solid experiences a sudden change in its thermal environment. Where it is applied, of course, there is a sudden change. There is a quenching process. Consider a hot metal forging that is initially at a uniform temperature, Ti, and is quenched by immersing it in the liquid of lower temperature at T infinity, and Ti is greater than, of course, T infinity. It means at higher temperature a certain metal and put into a very low temperature, that is T infinity, which is environmental temperature, or it put into the cold liquid or anything. If the quenching is set to begin at T is equal to 0, the temperature of the solid will decrease for time T greater than 0 until it eventually reaches to T infinity. Of course, the temperature of the solid is very high when put in the environment. Of course, at initial time it is T is equal to 0, the temperature is the temperature of the solid, and then with the time passes, the temperature is decreasing and eventually it reaches the temperature of the environment. This reduction is due to the convection heat transfer at the solid-liquid interface, of course. Let's say I've shown you this one. For example, this is the T infinity, which is less than the Ti, the liquid bath, and this is the metal which is at initial temperature is very high, right? And what will happen is put inside, and this is the red line is basically the surface where the convection will take place between the metal and the coolant. So the essence of the lumped capacitance method is the assumption that the temperature of the solid is spatially uniform. Spatially uniform means at different position it is uniform at any instant during the transient process. Only the temperature changes with time. This assumption implies that temperature gradient with the solids are negligible. So the main assumption is that the temperature gradient within the solid is constant, and the only the thing in which the body is basically cooling is with, or the solid is cooling with time, it is the time with it is cooling. That is the lumped capacitance model. So from Fourier law, heat conduction in the absence of a temperature gradient implies the existence of infinite thermal conductivity. Such a condition is clearly impossible because it's Ka dt by dx. If dt by dx is almost 0, it means the thermal conductivity is infinite, which is not possible. However, the condition is closely approximated if the resistance to conduction within the solid is small compared with the resistance to the heat transfer between the solid and the surrounding. So we can say that the resistance of the solid is very small as compared to the resistance of the solid with the surrounding, which is the convective heat, convective resistance. So the conductive resistance is very small as compared to convective resistance. So neglecting temperature gradient within the solid, so we can no longer consider the problem from within the framework of the heat equation. Of course, now we cannot apply the heat equation because there is no conduction. So the transient temperature response is determined by formulating an overall energy balance on the entire surface. The balance must relate the rate of heat loss at the surface to the rate of change of internal energy. What is the heat transfer from the surface of the solid and what is the internal rate of internal energy change? So minus E out, because energy is going out, is EST, energy stored or internal energy, or energy lost at the surface, plus change of internal energy is equal to 0. So this is do the convection, minus HAST minus T infinity is equal to the energy stored. It is MC delta T. So it is rho, V is the mass, the C is the capacitance, and dt by T, the temperature change with time. So by introducing temperature difference, we know that theta is equal to T minus T infinity. So hence d theta by dt is equal to dt by T at T infinity is constant. So we put this value of theta, of course, in this equation, in equation 5.2. So we'll get minus HAS theta rho Vc d theta by dt. Now by a variable separable method, and now integrate this by variable separable method by integrating theta I, of course, Ti minus T infinity. So by integrating I get minus T rho Vc Ash ln theta by theta I. To remove negative sign, of course, I just reverse the theta I and theta. So it's ln theta I by T, and this is the time taken to cool. And if I need to find theta I by theta, means the temperature difference relation. So it is, of course, exponent ASH rho VCT, AS surface area, H convective heat transfer coefficient, rho is the density, V is the volume, C is the capacitance, T is the time. So as you see, this theta I by theta is basically the exponential term. It is exponentially increasing. Or theta by theta I is equal to exponent minus, because if you change this one, then this becomes minus rho VCT ASH. So theta by theta I is T minus T infinity, Ti minus T infinity is equal to exponent minus rho VCT ASH. Now this is the equation number 5 can be used to find this equation can be used to find the time taken. Equation 5, this one can be time taken to cool, right? This one by solid to reach a certain temperature, and this equation 5.6 used to find the temperature reached by a solid after a certain time t. We know the environmental temperature, we know the initial temperature, and we know all these properties, material properties, and within the certain time we can find what the temperature reached by the solid. So equation 5.6 clearly shows that the difference between the solid and the fluid temperature decay exponentially and approaches to zero at T approaches to infinity. So this quantity rho VCAS may be interpreted as it is called thermal time constant. So rho VC is a rho VCAS. It may be taken as thermal time constant TT. Hence TT is equal to 1 over HAS rho VC. 1 over HAS we call as thermal resistance, and rho VC is CT is the lumped capacitance. RT is a convective resistance, and of course CT is the lumped capacitance. So we have developed the model, it's a lumped capacitance model. Now dear students, if you see this behavior from your previous classes, is very much analogous to the voltage decay that occur when a capacitor is discharging through a resistance in an electrical RC circuit. Okay, students, engineering systems are analogous. Analogous means their structure is different, but their function is similar. If you see this RC circuit from the previous classes, is the resistance and the capacitance. For that case, the charge stored or the charging and discharging of the capacitor is related with CVB 1 minus e raised to power minus t over RC. The only difference is that this R is electrical resistance, C is the capacitance of the capacitor, and of course VB is the voltage which is being applied. So how the capacitor is being charged and how the capacitor is being discharged, right? The Q becomes CVB when of course T approaches to infinity. So this transfer, which is analogous to charge, so this equation is similar. If you see, this one equation is similar to the equation we have obtained from the lumped capacitance. So to determine the total energy transferred Q occurring up to the some time t, we can write now in the analogous system like the capacitor. So Q is Q dt is HAS because the heat transfer is convection through 0 to t theta dt. And if I put the value of theta from this equation 5.6, sorry, this one, the theta is equal to theta I times this exponent term, and then of course we have this relationship. So minus HAS theta I, and I take the integral e raised to power this, and then the derivative of this to be divided by applying the 0 to t, I get the relationship. If you see, we get the almost same relationship here, only that rho v is the mass, of course C is the specific heat, and theta I is initial temperature, just like the VB in case of capacitor 1 minus e raised to power, and this one is the time constant, is RT and CT. This is RT and CT, right? So the quantity of heat should be related to the internal energy change of the solid. So minus Q is delta EST. Means for quenching, Q is positive and solid experience a decrease in energy. When you're doing the quenching process, cooling, and of course solid experience a decrease in energy. Energy contained within the solid because of higher temperature. And Q is negative, and the internal energy of the solid, of course, increases. Means you are putting a solid into a environment which is at higher temperature than the solid temperature. Now, this graphs is between, if you see the time and of course the theta by theta I, right? And you see the TT, the thermal time constant, temperature time constant, rho VC RCCT. And if you see, the larger the value of this temperature time constant, of course the theta by theta I is small. It becomes increasing, of course, with the larger capacitance temperature time constant. Of course, at the same, this value is increased. So we have to have a suitable criteria. But now the next thing is where this model, lumped capacitance model, can be applied, and where of course we cannot apply. To consider a steady state conduction through a plane wall of area A. Okay, although we have assumed that the steady state, but it can be applied to a transient state as well. So one surface is maintained at temperature at Ts1, one surface is maintained at temperature Ts1, the other is maintained at temperature Ts2, right? Ts1 is a higher temperature as compared to Ts2 and T infinity. We can say that Ts1 is greater than Ts2, and Ts2 is greater than the environmental temperature. So that this T2 temperature is in between Ts1 and Ts2. This equation clearly shows that if I think I will discuss this number later on. Hence, under steady state condition, the surface energy balance, we know that Ka by L Ts1 minus Ts2, right, and Ha Ts2 minus T infinity. This is the conduction within the metal, and this is the convection. So where K is the thermal conductivity of the solid. So Ts1 minus Ts2, just by rearranging, we get this RT of conduction or RT of convection. The conductive resistance to the convective resistance, and this becomes HL by K, and this is called Biot number. HL by K is a dimensionless number and is called Biot number. This plays a fundamental role in conductance from the surface. If you see this graph, if Biot number is very much less than 1, the temperature gradient is almost constant. But as the Biot number is increasing, right, if otherwise is equal to 1, you see it has a temperature gradient. Temperature gradient means temperature change with the position. And it becomes very large, and this, of course, gradient is very large. So from this figure, it clearly shows that this lumped capacitance model means the temperature gradient is negligible within this solid, can only be applied when Biot number is very much less than 1, which I'll just show you the HL by K. If you see, this is watt per meter square Kelvin, this is meter, watt per meter Kelvin, this is no dimensions, so Biot number is basically a dimensionless model. So what Biot number is giving? It's a measure of the temperature drop in the solid relative to temperature difference between the solid surface and the fluid. What is the temperature drop? Of course, within the solid, of course, and then it is relative to temperature difference between the solid surface and the fluid. So if Biot number I have already discussed. So hence the assumption of the uniform temperature distribution within the solid is reasonable if Biot number is very much smaller than 1. So what is the criteria? So people made this criteria like this. So Biot numbers HLC by K is less than 0.1. LC is basically the characteristic length, which can be found out by V by AS. For example, for a sphere, the volume is 4 upon 3 pi r cube. I just show you for one of the shape, and the later in a problem and example I've solved further. So surface area of the sphere is 4 pi r square, and if we cancel r by 3. Hence the temperature gradient within the solid is 0. By assuming the lumped capacitance model, if Biot number is less than 0.1. Now, exponent of equation 5.6, if I say HAST rho VC, because just to replace this one with a LC, you know that, of course, this becomes HT LC VC, right? Because LC is equal to V is equal to LCAS, so I replace with this, right? AS over V is basically LC by V, so it's cancel out, and in terms of LC it is HLC by K. If I multiply divide with K by LC, I get 1 over rho C LC. Just to show in this form, this is K LC by K, KT rho C LC square. Finally, alpha, we call alpha is equal to basically K by rho C. HLC by K is basically Biot number, and this alpha, this K rho C is called alpha T by LC square, we call it Fourier number. So it's very simple. So theta by theta I is equal to T minus T infinity is Ti minus is exponent minus Biot number times the Fourier number. This is another relationship in terms of both of them, Biot number and the Fourier number are dimensionless number. This is the figure which I am showing you for your information, that for example this is a solid wall and this is maintained at temperature T infinity, and then a solid wall has at a certain temperature, and if you see, if this is the temperature gradient is 0. As long as the Biot number is increasing, you see that there is the Biot number is very much less than 1. In this case, of course the temperature gradient is almost 0. But if Biot number is equal to 1, and of course there is the see the temperature gradient, temperature is changing within the solid, within the wall along the x. And if it is very large, and of course then it becomes almost a parabola, right? And that is a large temperature variation with respect to with respect to this to position. Let's see one of the examples we'll solve today. Thermocouple junction, which may be approximated as a sphere, is to be used to temperature measurement in a gas stream. The convection coefficient between the junction surface and the gas is H is 400 watt per meter square, and the junction physical properties K is 20 watt per meter Kelvin, capacitance is 400 joules per kilogram Kelvin, and the density is 8500 kilogram per meter cube. The question is to determine the junction diameter needed for the thermocouple to have time constant of 1 second. If the junction is at 25 degrees centigrade and is placed in a gas stream that is 200 degrees centigrade, how long will it take for the junction to reach 199 degrees Celsius? We are given the H, K, rho, time constant, initial temperature, T in is basically 25 degrees centigrade, T infinity is 200, and of course the time to reach 199 degrees centigrade is to be find out. As we know the junction temperature and diameter is unknown, so how to check the criteria? First of all, and then after the criteria we can move forward. To show so how to check with that, of course, AS surface AS. I'm sorry, this is VS, sorry. This is the volume, 4 upon 3 pi r cube. So 4 upon pi, and it is d by 2 whole cube. This becomes pi d cube by 6. This is of course volume. And this area, surface area, is of course 4 pi r square is pi d square. We know that the temperature time constant is 1 by HAS, it's times rho VC. So we have the values. So this is V is equal to pi d cube by 6, and then C, and we put the value of AS, which is pi d square. Just place the value of volume and the and the surface area. We get the temperature time constant. As by simplification, I get TT is rho dc by 6h, and then diameter is this. As I know the temperature time constant, I can find the diameter, which is about 7.06 x minus 4 or 0.706 millimeter. Now you should check, because I find the diameter and now I check why the Biot number is within the limits or not. So the characteristic density is V by AS, which is equal to R by 3, and Biot number is HLC by K. So this I put the values 400.353 x minus 3, and the 3 times 20, which was 3 this one, and this 20 is the convective heat transfer coefficient. Sorry, thermoconductivity, and we get 2.35 x minus 3. This is less than 0.1. Hence, here the lambda conversion model is applied, and the diameter we have found is correct. Now, from equation 5.5, we can find the time T to reach the gas to a temperature at 199. This is another question. So T is equal to rho is pi d cube by 6c h pi d square. I replace the volume and the surface area, ln Ti minus T infinity. That equation we have already discussed. It's rho dc, and we know the value of rho, right? Rho, diameters, capacitance, everything is known, and we know the Ti is 25, and of course the T infinity is 200. The T that we need is 199 minus 200, and that gets 5.2 seconds, which is almost 5 times of the temperature time constant is required to reach that particular temperature. Okay, dear students, this completes my lecture number 8. In the next lecture, I will talk of more examples and also solve the unsolved problems regarding the lumped capacitance model, and this chapter will be completed for our studies at the course that we have described in this. Thank you very much.